Hi everyone, this is the second of the two videos covering sedimentary rocks. And at the end of the last video, we discussed in a fair amount of detail the fact that three important sediment characteristics change in a systematic way as we move increasingly downstream. So from left to right in this diagram, as we move from the alluvial fan environment to the stream environment, to the beach and the delta environment, and then ultimately even further offshore into the nearshore shallow marine environment and ultimately the offshore deep marine environment, we find that the characteristics of detrital sediments change in a predictable, systematic way. Namely, grain size decreases as we move downstream, that is, the size of the fragments gets smaller. The shapes of the fragments changes as well. The shapes become more rounded in the downstream direction. And then finally, grain size similarity, what we described as sorting, also increases along with rounding. Remember, sorting is just how similar the different grain sizes are in a detrital sediment. So, for example, a trash can full of BBs would be a well-sorted deposit, whereas a trash can full of BBs and baseballs and softballs and walnuts and marbles would be a poorly sorted deposit because there's so many different sizes represented. Okay, so the real advantage of this then is that when we find detrital sedimentary rocks in the rock record, just by paying attention to characteristics like grain size and rounding and sorting, we can, in a general way, get a sense of whether that sedimentary rock formed in an upstream environment, like an alluvial fan or a stream environment, or perhaps more of a downstream environment, like a beach or a delta environment. And obviously, there are other clues as well. If we find marine fossils in the detrital sedimentary rock, then we of course know it formed in a marine environment. Whereas if we find, land-loving organisms like dinosaurs in the sediment, we know it was more of a non-marine deposit. But for now, we really just want to focus on what grain size, rounding, and sorting are in effect telling us with regard to where the sedimentary rock formed. And by where in this case, I generally mean, did it form in more of an upstream environment or more of a downstream environment? That's what things like grain size, rounding, and sorting will tell you. We also often speak in terms of environmental energy as geoscientists. And this just means sort of how swift and turbulent the currents are in that environment where the sediments are being deposited. So in upstream environments like alluvial fan and stream environments, we often characterize these kinds of environments as being high energy. And that just means that we have swift, turbulent currents in places like that. Imagine the sort of swift running stream. You might have rapids, you might have waterfalls, and the currents are going every which way. They're obviously very turbulent. So that would be an example of a high energy environment. On the other end of the spectrum, imagine the middle of a lake or out in the middle of the ocean or perhaps the middle of a lagoon. You have really gentle currents. The water isn't very turbulent. It's somewhat stagnant. It just kind of sits there. That's what we mean by a low energy environment. And guess what? We see different kinds of deposits in high energy versus low energy environments. Let's go back to that high energy environment for a second. Because the currents are so swift and turbulent and constantly changing in that environment, for the most part, it's only the big stuff that can settle out of all that swiftness and all of that turbulence. And so, in general, high energy, that is upstream environments, are going to be characterized by relatively large grain sizes, relatively poor rounding, and relatively poor sorting. This is because often these upstream high energy environments represent the first or initial dumping ground for sediments that are maybe flowing out of some mountains, for example. So the particles haven't had much time to become well sorted. They certainly haven't had much time to break down into smaller pieces. And they also haven't had much time or much opportunity to have their corners and edges chipped off to become more round. All right, now at the other end of the spectrum, if we go out to the middle of a lake, the currents are not swift at all out there. It's pretty much stagnant water, or at most the currents are very gentle. And so under those low energy conditions, it's even the fine stuff, or especially the fine stuff that can kind of settle out of suspension to coat the bottom of the lake in this case. Why don't we get bigger stuff in bottom of a lake, out in the middle of the lake? The reason is the bigger stuff would have already fallen out. It would have already been deposited along the lake shore, perhaps as the stream flowed into the lake and maybe formed a delta right there where the stream entered the lake. But out in the middle of the lake, it's only the really fine, small particles that have the opportunity to settle out of suspension, therefore coating the bottom of the lake with fine grain detrital deposits. Okay, back to grain size. You don't need to actually know this chart. There are no numbers to memorize on this chart. I just want you to appreciate that we have a sort of formal way of describing different particle sizes. And this is not something you need to memorize. I just want you to appreciate that a boulder is a larger particle size than a cobble. A cobble is larger than a pebble. Boulders and cobbles and pebbles are collectively referred to as gravel. And then, below gravel, meaning if the particles are, in this case, less than 64 millimeters in diameter and more than about a 1/16 of a millimeter in diameter. So we're in this sort of middle portion of the diagram, right in here. We're dealing with sandy deposits, right in here. And then below that, if our particles are smaller than a 1/16 of a millimeter, but larger than 1/256th of a millimeter, then that's the formal definition of what we call silt as geoscientists. And then below that, if our particles are really small, then of course we're in the clay range. And you can see how small clay particles are. They're less than 1/256th of a millimeter. That's really small. And then what might not be clear in this diagram, let me clear away some of the annotation, is silt and clay collectively are known as mud to geoscientists. So a simpler way to think about it is that you have sort of three size fractions in a typical detrital sediment. Gravel being the biggest stuff, sand being the intermediate stuff, and mud being the small stuff. So these are all sediments. And then imagine now if we turn those loose sediments into hard sedimentary rock. And that's what's listed on the right here. So conglomerate and breccia are made out of gravelly sediments. If the clasts, the fragments, in other words, are rounded, then we say that it's a conglomerate. If the gravel clasts are still kind of sharp and angular with edges and corners, then that's what makes a sedimentary breccia. And then on down, if the fragments are mostly sand-sized, we would call that rock sandstone. If the fragments are mostly mud-sized, we might just generically call it mudstone, or if it turns out that most of the fragments are in the silt size range, then of course we'd call it siltstone, or perhaps claystone if it's mostly made of clay. Shale is a particular type of mudstone where the layers are really, really thin. Think of shale as a thin-bedded mudstone. Okay, so here's more of a visual. We described this in more detail in the first video, but this is a nice visual to demonstrate rounding and sorting. So you can see in that upper row there, a very poorly sorted sediment, or a poorly sorted sedimentary rock for that matter, contains a wide range of clast sizes. A clast, by the way, is just a grain. It's another term for a grain or a fragment. And then down below that, the bottom two rows kind of give you a sense of how we distinguish angular from subangular, from some rounded to rounded deposits. Again, we're not going to go into this level of detail on this course. I'm not going to ask you to identify, a subangular versus an angular grain, for example. But again, just appreciate that as we move downstream, thanks to increasing abrasion during downstream transport, a detrital sediment will become better rounded and also better sorted as well. All right, well, now that we've talked a lot about sediments and depositional environments, what actually happens to create a sedimentary rock? Well, first thing we need to do is to break down pre-existing rock. That's, of course, what weathering is all about. That's why I've listed it first. But then streams typically, but it could also be glacial ice and even wind, needs to then erode that weathered material. And by erosion here, we just mean that the weathered material that's sort of sitting there at the outcrop gets caught up into the current and carried along. So think of erosion as the mobilization of weathered material. And then once that weathered material is added to the flow, whether it be a stream or the wind or a glacier, that material, that eroded material, then gets transported increasingly downstream. Eventually, though, due to changes in current speeds, the material that was being transported by the fluid, either the wind or the water or the ice, goes away, or at least slows down, and material that was being carried along by the current can settle out to collect somewhere. That's what deposition is all about. At this point, when we're still in the upper row here, we're still talking sediment. We haven't yet turned that sediment into a sedimentary rock. The very last step involves both compaction and cementation. Those two terms collectively are what we mean by lithification. Think of lithification simply as the way that Mother Nature turns a sediment into a hard sedimentary rock. And just because we're burying earlier sediment underneath later sediment, the weight of the later sediment to some degree compacts the earlier sediment. There's compaction. Particularly for larger sand to gravel-sized deposits, compaction alone will never fuse the particles into hard rock. For that, you need cementation. And in this case, what's happening is chemically laden groundwater is moving through and between the sediment grains, and it's leaving behind minerals that act as a geologic glue to stick the sediment together to itself. A good analogy might be peanut brittle. Think of the peanuts in this case as clasts, as the sedimentary clasts, and think of the candy in between the peanuts, the brittle part, if you will, as the cement, the sedimentary cement that in effect glues the particles together. So in summary, that's how you make a sedimentary rock. First by weathering pre-existing rock, and then by eroding and transported that weathered debris away from the site of weathering. Eventually, Mother Nature dumps that weathered debris somewhere, that's deposition, and ultimately turns that loose sediment that's now been deposited into a hard sedimentary rock via compaction cementation. That's what lithification is all about. All right, now we're going to get into the details of how to formally name and classify a few examples of common detrital rocks and common chemical rocks. And just to further emphasize the point, detrital rocks, they're composed of rock fragments. So guess what? We name and classify and distinguish detrital sedimentary rocks based on the fragment characteristics, whether they're gravel, sand, or silt and clay sized, and in some cases, their shapes, whether the fragments are rounded or more angular. And then on the bottom of this diagram for the chemical rocks, in this case, because the chemical rocks are just made out of chemical residues that may have accumulated as a result of evaporating water, for example, or maybe by the action of biological life forms, then we're dealing with chemical residues here, whether biological or whether inorganic, and these precipitated, that is chemically deposited chemicals, ultimately can be lithified into chemical sedimentary rock. And in this case, we're classifying the chemical rock mostly based on its composition. So obviously, rock salt has a very different composition than limestone, which in turn differs from chert and coal. All right. Well, what are the different components of a sedimentary rock? We've alluded to these already, but let me make it more explicit. Particularly if we're talking about a detrital sediment composed of fragments, then the larger clasts, the ones that are settling out of the water, for example, those are the larger fragments that we call clasts, the larger rock and mineral fragments. And then very often in between these larger clasts, we have a sort of second population of smaller clasts, smaller rock fragments in between the larger clasts. This is definitely going to be true. It's mostly going to be true for poorly sorted deposits. Those smaller particles are called matrix because they occur in between the larger particles. And then as we talked about, if there's some kind of mineral glue that is cementing the clasts and the matrix together, that's the sedimentary cement. And there are common forms of sedimentary cement, including quartz. When quartz is precipitated between larger grains, then quartz would be a common sedimentary cement. Also rust, iron oxide can be a sedimentary cement when it forms. Calcite is a calcium carbonate mineral, and it's a mineral that, even though it's not a silicate mineral, is really, really common in most geologic environments. And so very often for detrital rocks, we find that calcite is the main cementing material. And even clay minerals can represent the cementing material, kind of gluing the other grains together. So here's a quick visual of the three different components of sedimentary rocks, including clasts, those are the larger grains, matrix, those are the smaller grains in between the larger grains, and ultimately cement. Think of cement as itself a chemical residue deposited in between the matrix and the clasts that literally glues the rock together. And there in the bottom diagram, you're actually looking at a photomicrograph, an actual photograph of a detrital sedimentary rock in terms of what it looks like under the microscope. Okay, well, I just want to finish up this part of the lecture with a few examples of common detrital and chemical sedimentary rocks. Here's what conglomerate looks like. It's a pretty gravelly rock, but what makes conglomerate is two things. The fragments are gravel-sized typically, or at least it's the gravel fragments that dominate the rock. Obviously there's going to be some matrix as well mixed in with the gravel fragments, but also that the gravel fragments are relatively rounded. So that really is what makes a conglomerate, the fact that the fragments are gravel-sized and the fact that they're rounded. And then a related rock, that, by the way, is what conglomerate looks like, close up, maybe through a hand lens. And a related rock would be a sedimentary breccia. And the only difference between breccia and conglomerate is that whereas conglomerate is composed of rounded gravel fragments, breccia is composed of relatively angular gravel fragments. So you can see in this slide that the gravel-sized fragments in this specimen of breccia have corners and edges. So they're angular as opposed to rounded. Just a quick example of what sandstone and conglomerate look like in the field. That upper layer that my hat is sitting on from about here all the way up to here, this is an alluvial fan deposit. And you can see it's very gravelly. In fact, it's the gravel and cobble fragments that really dominate this rock. And so on that basis, that upper layer would be a conglomerate. And then down here, underneath the upper layer, the slightly older layer consists mostly of sand-sized grains. And that's going to be sandstone once the grains become lithified. This is often a field trip locale for me and my students. This is Tourmaline Beach in northern Pacific Beach, and we're looking at the exposed cross section of a sea cliff just north of the parking area at Tourmaline Beach, and you can see this sort of smiley face channel deposit, which is composed of cobbles and gravel-sized fragments that we call conglomerate. And then on either side of the conglomerate, we have slightly finer material that we would call sandstone. There's what siltstone looks like in hand specimen. It's pretty fine. You can't really see individual clasts with the naked eye typically for siltstone, but you can kind of feel them. Siltstone feels kind of gritty, particularly if you chew a little bit between your teeth. And then even finer than that, we have a typical mud rock. This would be a thin-bedded mudstone known as a shale. And shales are typically mixtures of silt and clay. And again, the thing that makes a shale, other than the fine clast sizes, the silt and the clay-rich nature of this deposit, is that it's very, very thin-bedded. The layers are very thin. So think of shale as a thin-bedded mudstone. And shale is a very common detrital sedimentary rock. It occurs in a variety of different depositional environments. In lake environments, you often develop shale also in lagoon environments. And shale can be both a marine and a non-marine sedimentary rock. Obviously, in this case, the specimen that we're looking at here would be a non-marine shale, probably accumulated in like an ancient swamp or something like that, judging from the fern fossils in the shale. This is a type of limestone known as coquina. It's just kind of a shell hash limestone. There's my ring for scale. So this is a close-up, and you can see these beautiful scallop fossils all around. The scallop fossils obviously are just the skeletal material of ancient organisms, namely scallops. And what the scallops do to make their shell is they secrete calcium carbonate. And in this case, their skeleton is on the outside of their body. And then when the organism dies, the hard part, the shell in this case, is often preserved. And so if you have a whole deposit, just sort of a mishmash of shells and shell fragments, all of which are made out of calcium carbonate, then we would call that kind of chemical rock limestone. And because all the limestone is composed of shell fragments, we would further refer to it as coquina limestone. This is chalk. These are the White Cliffs of Dover in England. And chalk is also a form of limestone because it's made out of calcium carbonate. CaCO3 is calcium carbonate. Think of chalk as just a fine-grained biochemical limestone. And if you were to look at this chalk under a really high-powered scanning electron microscope, you'd likely see two different kinds of marine organisms, foraminifera and also coccolithophores. These are both kind of free-floating organisms that live in the sea, and kind of like scallops, they make their hard parts out of calcium carbonate. And then when the organism dies, after it's been freely floating in the seawater, the skeletal material that the organism created during its life sort of sinks down to the sea floor and coats the sea floor with a calcium carbonate rich deposit that when it becomes lithified, we refer to as chalk. This is chert. Sometimes you'll hear chert less formally referred to as flint. You might have heard that term. Flint, or more broadly chert, is just a silica-rich chemical sedimentary rock. It's made out of nothing but silicon and oxygen. And it too contains tiny, small fossils, typically. And often what you'll see in chert are tiny, microscopic, in many cases, life forms that in this case make their shells out of silica, silicon and oxygen. And one type is known as a radiolarian. That's on the left. Radiolaria would be plural. And then on the right are a type of algae known as a diatom. Here again, diatoms and radiolaria make their shells out of silica. And then when they die, that silica particle sinks down to the bottom of the sea to accumulate as a silica-rich deposit that, when it becomes lithified, turns into a kind of a hard, almost glassy-looking rock called chert. And then, of course, as you know by now, it's possible to have material that we think of as a sedimentary rock that's composed of organic material, in this case just compressed carbonized plant matter. That's what we call coal. Coal typically forms in kind of temperate to warm tropical climates and swamps where there's a lot of vegetation, and typically the vegetation grows and dies and gets buried so quickly that microbes don't have enough time to completely recycle it back into the environment. And so you end up with this carbon-rich layer that, with a little bit of heat and time and compression, can turn into coal. This is a photograph I took a few years ago. I was visiting Ireland and happened to see a really nice example of an Irish peat bog, essentially almost like a swamp. And all that's happening here is, grass is growing and dying so rapidly that it gets buried before microbes can break it down. And at first, you end up with just a tangle of roots and organic matter. That's called peat. And then if that peat were to be buried a little bit and lithified, it would progressively turn into coal. But I'm showing you this slide just to emphasize that what you're seeing is literally the kind of depositional environment that coal forms in. What I'm showing you here isn't coal yet. It might take a few tens of thousands of years in deeper burial before this peat turns into coal. But this is the sort of environment where we expect coal to form. Rock salt. Rock salt, as we talked about, forms in playa lake environments where maybe you have a saline lake that periodically evaporates and leaves a residue of salt behind on the lake bed. So that's what we're seeing here. Over in the bottom right-hand corner of the diagram, we're actually seeing an image that oil companies used. This is used by bouncing energy waves into Earth's interior. And in this case, they're bouncing out off of this subsurface structure known as a salt dome. So here's the salt, something like that. That's all salt. And then what's happened in this case is under pressure, the salt becomes kind of like silly putty, and so it's kind of being squeezed upward as a plastic. And then these more horizontal layers on either side of the salt dome represent different kinds of sedimentary rock, maybe sandstone and shale. And the reason the oil companies are very interested in salt domes is kind of, as you can see in the lower left-hand diagram, it's common to find oil deposits on the margins of salt domes if the geological layering is correct. And in this case, we have a source rock looking on the lower left-hand diagram. The source rock would be an organic rock that the organic material is forming in the first place, and then eventually the organic material kind of breaks down, turns into like a gloppy liquid, petroleum hydrocarbons. And in this case, the petroleum hydrocarbons, because they're buoyant, are migrating out of the source rock and into the reservoir rock. This sort of sludge, if you will, this liquid sludge is filling up the spaces between the sand grains in the sandstone. And then the third thing you need to really accumulate these pools of oil is you need a cap rock, and that's what the shale is doing here above the salt dome. The cap rock, in effect, prevents the light, buoyant oil from migrating all the way up to the ground surface. And it's under those conditions that you can accumulate big, thick deposits, big, extensive pools, if you will, of subsurface petroleum hydrocarbons. And of course, that's what the oil companies are interested in. Okay, let's do a couple quick Zoom polls. We'll just kind of do these virtually. Which sedimentary rock would you expect to form in a high energy upstream environment. So I'll give you a second to kind of decide that one. What do you think? Remember, high energy means swift, turbulent currents. It's only the big stuff that can settle out of that high energy situation, and so it's going to be conglomerate that forms in a high energy environment. How about this one? Which sedimentary rock would you expect to form in a low energy environment, such as the middle of a lake? Here again, low energy, very calm currents. It's only going to be the tiniest particles that are able to kind of make it out to the middle of the lake before they settle. And so, we might expect a fine-grained detrital sedimentary rock like shale to form out in the middle of a lake. How come we're not getting bigger stuff out here? As we talked about earlier, it's because the larger stuff is going to fall out when the stream first enters the lake, and perhaps we might even get a delta deposit on the lake shore, whereas, and this might be maybe sandstone once it lithifies, whereas out here we're going to get mudstone or perhaps shale in the lower energy environment. Okay, I was saying before that limestone in particular typically forms in warm, shallow, well-lit seawater, and just like you're showing here, typically we see coral reefs develop on planet Earth within maybe 20, 30 degrees of the equator, and so this gives us a sort of clue as to interpret ancient coral reef deposits. And so even if we look in the geologic record and we're finding coral reef deposits that are 500 million years old, we can pretty much assume that back when that limestone was first developing, way back 500 million years ago when it was a coral reef, that coral reef would have been forming, within 20 or 30 degrees of the equator. So there's a latitudinal control, if you will, on the deposition of skeletal marine limestone. Okay, I'm going to cover this topic pretty quickly because it's not one that's going to be emphasized too much. But in addition to things like fossils and grain size and rounding and sorting, we can pay attention to other characteristics of the sediment as well. These are what are called sedimentary structures. And just very quickly, the layering in sedimentary rocks comes from the settling out of particles. That layering, that sedimentary layering, is called bedding. Whenever we see these inclined sort of sweeping layers in sandy deposits, that's going to be indicative of ancient fossilized sand dunes. That's called cross-bedding. Imagine that you have shallow water flowing over typically a muddy substrate. If the water is just the right depth and flowing at just the right speed, it might kind of deform the surface of that muddy substrate into a series of ripples. And then if those mud ripples harden into mudstone, you have a sedimentary structure called a ripple mark. Maybe we have a lake that evaporates to create a playa, and then maybe the mud on the surface of the playa evaporates and cracks and shrinks as it desiccates, creating mud cracks. Even mud cracks can be preserved in the geologic record, particularly if you deposit some other mineral or some other sediment inside the cracks. That's how you preserve mud cracks. And whenever we find them in sedimentary rocks, they're going to be indicative of drying. So the fact that a mudstone shows evidence of mud cracks, from that, we're going to be able to infer that that was an area that was subjected to periodic wetting and drying, an environment such as a playa lake, for example. Let's see. For now, I'm going to skip imbrication because we'll see an example of that. And trace fossils, I'll show you some example of that as well as we kind of proceed here. This is just kind of a quick list. Now we'll look at some examples. So that's what bedding looks like. Simple horizontal layering. That's the main sedimentary structure that we use to recognize sedimentary rocks in general. And then here are those kind of inclined sweeping layers that we talked about earlier. Again, those are called cross beds, and they're indicative of ancient fossilized sand dunes. Here, wave ripple marks. In this case, the ripple marks are symmetrical on either side, as you can see in the cross section in the upper right. And so that's going to indicate so-called bidirectional currents moving kind of back and forth, the sort of sloshing back and forth environment created by waves. It's also possible, though, that our ripple marks can be asymmetrical. The downstream face of the ripple mark, in this case, is a lot steeper than the upstream face. And that is a paleocurrent indicator. From the asymmetry of the ripple mark on this ripple marked mudstone, we can actually tell which way the water was flowing to create the ripples. So that's pretty interesting because it allows us to reconstruct an important characteristic of this ancient environment, namely which direction was downstream. Good example of both modern and fossilized mud cracks. Again, the reason you can see these mud cracks on the right is that other sediment has filled in the cracks, and that sediment ultimately got lithified into a sedimentary rock, thus preserving the mud cracks. Here's what imbrication is. Think of imbrication as a sort of natural domino style alignment of fragments. And in this case, all of the fragments are sort of flopping over to the left. There's my Hapfer scale. This is a cross section of an alluvial fan deposit. And from the orientation of the long axes of the fragments, we're able to tell which direction was downstream. So kind of like those asymmetrical ripple marks, imbrication can tell us something about ancient currents, that is paleocurrents. So a trace fossil is essentially indirect evidence of ancient life. In this case, we're looking at an actual footprint of a dinosaur, but not the dinosaur skeleton itself. So this is why we would call this preserved dinosaur footprint a trace fossil as opposed to an actual fossil. There's no part of the dinosaur left. The dinosaur, in effect, made a trace of its presence in this ancient sandstone, in this case. Okay, well, finally, kind of to zoom back out to the big picture, you might remember in this class that uniformitarianism is one of the two big ideas around which we're structuring the entire course, along with plate tectonic theory. And sedimentary rocks are a perfect example to discuss uniformitarianism. And in this case, the way we interpret sedimentary rocks is from left to right in the diagram. So beginning on the left, this is why we study modern depositional environments as geologists, is we can understand how things like grain size sorting and rounding, change with downstream transport. Then what we do, once we've sort of calibrated in our minds what modern depositional environments look like, we then go back and we study the rocks in the middle column there. And we pay attention to things like grain size, rounding, and sorting, the composition of the sediment, the presence or absence of any sedimentary structures, et cetera. And then, in effect, now that we've studied both the present and the past, we can infer characteristics about the past in light of our study of modern depositional environments. So by studying modern depositional environments, and then studying the ancient rock record, this allows us in that third column over to infer characteristics of ancient depositional environments. In other words, we're using our understanding of the present to make sense of the past when it comes to depositional environments, sediment characteristics, et cetera. So it's yet another demonstration of how the present is in many ways the key to understanding the past. And then I'll just conclude with a brief reminder of the really important points in both of these videos that cover sedimentary rocks.